Let's do an example. Suppose we have a set of data x1, y1 through x6, y6 as follows. x1 is 1, 3, x2 is 2, 3, x3 is 2, 4, x4 is 3, 1, x5 is 3, 2, and x6 is 4, 2. With y1 equals to y2 equals to y3 equals to k1, which is 1, and y4, 5, and 6 are k2, which is 2. Apply linear discriminant analysis by doing the following. A. Find estimates for the linear discriminant functions delta 1 and delta 2. Find the line that decides between the two classes. And C. Classify the new point 5, 0. If we plot the points, we get this. Okay, so here we have x1, x2, and x3, and x4, 5, and 6 here. So we expect the decision boundary to be a 45-degree line here, right, separating the two classes. Okay, the number of features, P, is 2. The number of classes, big K, is 2. The total number of data points, big N, is 6. The number N1 of data points in class K1 is 3. And the number N2 of data points in class K2 is 3. First, we will find estimates for pi 1 and pi 2. Okay, let me write that. Pi 1 and pi 2. The prior probabilities that y equals to k1 and y equals to k2 respectively. Then we will find estimates for mu1 and mu2. The class-specific mean vectors. We can then calculate the estimate for the covariance matrix sigma. Okay. Finally, using the estimates pi 1 hat, pi 2 hat, mu 1 hat, mu 2 hat, and sigma hat. Okay, using these estimates, we can find the estimates for the linear discriminant functions, delta 1 of x, and delta 2 of x. Okay, we can find estimates for these. Okay. Pi 1 hat is given by n1 over n. So that's equal to 3 over 6. And that's 1/2. Pi 2 hat is n2 over n, so that's 3 over 6. And that's 1/2. Mu 1 hat is given by 1 over n1 sum of xi, where I ranges over all those points where yi is 1. Okay, so that's equal to 1 over 3 times, now all of those xi such that yi is 1. So those are the first 3 points, x1, x2, and x3. Okay, so we add those up, divide by 3. We get this. 5/3 and 10/3. Similarly for mu sub 2 hat, that's 1 over n2 sum of xi where the class is 2. So those are the last 3 points. x4, x5, and x6. Okay, simplify. We get this. And sigma hat is given by 1 over n minus k sum over k sum over I, yi equals to k. This, plugging in the values for n and k, I get 6 and 2. Sum as k ranges from 1 to 2. And the same stuff here. Plugging in what we got for mu sub 1 hat and mu sub 2 hat, we get that sigma hat is this. Simplifying, we get this. Okay, so we have sigma hat. Now we can find the inverse. And we get this. Okay, now delta 1 hat of x is given by this formula here. So that's equal to x transpose times this. If we multiply all of that out, we get 0, 10 minus 1/2. This stuff here, you can calculate that to be 100 over 3. And pi 1 hat was 1/2. Okay. Now let's write this in terms of the components of x. So that's 0, 0x1 plus 10x2. Okay. Simplify this. Okay, this is what we get for delta 1 hat of x. Delta 2 hat of x is given by this formula. Okay, pretty much the same thing, except we have 2's everywhere here, mu sub 2 and pi sub 2. So that's x transpose times 10, 0 minus 1/2 times, okay, multiply this out, you get 100 over 3. And pi sub 2 hat was 1/2. Okay, so this becomes 10x1. Reduce this. Okay, so this is delta 2 hat of x. Now, setting delta 1 equal to delta 2, we get this equation. Okay, now these constants cancel out. So we get 10x2 equals 10x1. Divide the 10 out. We get x2 equals x1. Okay, so the line that decides between the two classes is given by x2 equals x1. Okay, let's graph that out. So here's the line, x2 equals x1. Here are the data points. And you can see that it separates them like so. Okay. Now if delta 1 hat of x is bigger than delta 2 hat of x, then we classify x as of class K1. So if x is above the line x2 equals x1, then we classify x as of class K1. Conversely, if delta 1 of x is less than delta 2 of x, then we classify x as of class K2. Okay, this corresponds to x being below the line x2 equals x1. Okay, now the point 5, 0. 5, 0 is right here. Okay, and it's below this line. So we classify it as of class K2.